So what is an equivalent circuit? Equivalent circuit of any electromagnetic device is the circuit representation of the equations describing its behavior or performance. Okay, so by using this circuit model, we can study or analyze any electrical machine using circuit theory model or circuit theory only. Okay, so here any the equivalent circuit of any electromagnetic device consists of this combination of these resistances, inductances, capacitances and voltages and some other elements also. So it is a very simple representation of any uh, complicated electromagnetic device. We can apply only where we can apply circuit theory. Okay, we can apply also the field theory model, but the only this circuit theory model is sufficient to study or analyze any electromagnetic device after we getting this equivalent circuit. Okay, so it is a simplified version of any electromagnetic device. So this diagram shows the exact equivalent circuit of a single phase transformer where this exciting current is neglected. Okay, you can see the all the parameters of a single phase transformer are shown here. That is two windings N1 N2 and the winding resistances R1 R2 and the leakage reactances X1 X2. These are shown in this diagram. Only the exciting current is not shown. So here I1 is the primary current, I2 is the secondary or load current, V1 is the applied voltage, V2 is the voltage across the load, and here I1 contains only the load component, no exciting current. E2 is the induced EMF across the secondary winding. V1 dash, which is equal to minus of E1, is shown here. Okay, so in this diagram, that means the equivalent circuit we can define as a circuit representation of the equations describing the performance of the transformer. So what are the two main equations for a transformer? One is the expression of V1, another is the expression of V2. So we can write, we have studied or derived these two equations from our previous discussions. So we can write V1 as V1 dash plus I1 into R1 plus JX1 or Z1. Okay, I1 into Z1. So I1 Z1 is the voltage drop across the leakage impedance. If we add this with the voltage drop across the uh, winding in the direction of current flow, that means the primary current I1, then we have one voltage, that is V1 dash, which is equal to the induced EMF but in opposite direction. So if we add these two drops, not drops, V1 dash is the voltage drop, but actually it is the voltage, induced voltage but in opposite direction. So if we add these two voltages, then we will get the applied voltage V1. So this is one voltage equation. uh, this is the voltage equation for the primary side. So if we want to draw the circuit model for this equation, then we have to use the left hand part of this figure, that is V1 is the applied voltage. So this is a voltage rise, then one voltage drop which is I1 into this impedance, then again another voltage drop, but it is in opposite direction, which is E1. Okay, so V1 dash is equal to minus of E1. So if we write E1 here, so that will be a voltage rise. Okay, so in that case the equation will be V1 plus E1 is equal to I into R1 plus JX1. but we don't require that concept here. We only write the circuit theory equation. Okay, so for that we need this equation v1 equals to v1 dash plus I1 z1. And for the secondary side we can write the expression of E2 in terms of the voltage drop across the load and the voltage drop across the secondary leakage impedance. So V2 plus I2Z2, these two drops will be equal to the induced EMF across the secondary side. So here in this equation no exciting current is there. So this is the exact equivalent circuit of a transformer where the exciting current is neglected. Okay. Now in this diagram the exciting current is included. So we have one parallel branch or shunt branch through which this exciting current will flow, and we know that exciting current has two components. One is core loss component which flows through some resistive element RC, and the other is magnetizing component which is in phase with the flux produced by this exciting current but in quadrature with the voltage V1 dash. So if we divide this V1 by the reactance Xm, then this current Im will lag the voltage by an angle of 90 degree. That is why this complex notation J is required. So V1 dash by Jxm is equal to Im. Okay, so that is why this component is considered, this component is considered as the reactive component, because the current flowing through this path lags the voltage V1 dash by an angle of 90 degrees. So this is purely inductive, but the current IC, this current is in phase with V1 dash, so this element must be a resistive element. Okay. The rest of the things remains same. So here the equations will be V1 is equal to V1 dash plus I1 plus R1 plus Jx1, and V2 that is equals to V2 plus I2Z2, that is equals to this E2. And for these branch, IE is equal to V1 dash by RC, and IM is equal to V1 dash by Jxm. Okay, and IE, sorry, this component is IC. IE is equal to IE plus IM, and I1 is equal to I1 dash plus IM, sorry, IE. So I1 dash is the load component of primary current, which is actually related with the secondary current I2 as I1 dash N1 is equal to I2 N2. Okay, so these are the describing equations based on which this equivalent circuit can be drawn. Now you can see the windings are shown by dotted lines. These are dotted lines. Okay, so why these dotted lines are used? Because this is the ideal transformer. These two windings N1 and N2 are now showing only the ideal transformer. Why? Because all the imperfections from a practical transformer are removed and they are represented separately. See, first R1, that is the winding resistance of N1. This is here, it is shown. So in this winding no resistance is there. Jx1, that is the leakage reactance. Leakage reactance is produced by the leakage flux. So X1 means related to primary winding. So leakage flux produced by primary winding, that is phi L1, that is represented by this Jx1. So again that is separately shown. So in this winding there is no leakage. Now core loss is shown by this part, so no core loss is there in this winding. Okay, so again secondary side, R2 is secondary winding resistance, Jx2 is secondary leakage reactance, and exciting current part, that means core loss part, core is common to both, so only this RC will be sufficient to represent the core loss. Okay, so this section is nothing but an ideal transformer. It has no winding resistances, no leakage reactance, and no core loss. Okay, so this is an ideal transformer. This is shown only to show the transformation of voltages and current. Okay, there is no other cause to show this ideal transformer, other reason to show this ideal transformer. Okay, all the imperfections are shown separately. Imperfections of a practical transformer are shown separately in this equivalent circuit. So these two windings only represent the transformation of voltages and currents. That is why it is drawn by dotted lines. Is it clear?
Yes, sir.
So you have to draw these two windings by dotted line, and you have to indicate that this is the ideal transformer without having any winding resistances, no and leakage reactances, and no core loss also. Okay. So here the descriptions are given. So primary current has two components. One is I1 dash, which counteracts with the secondary load component, load current. So I2 N2 is equal to I1 dash N1. I have already shown I1 dash N1 equals to I2. This is the load component of primary current I1. Another component is IE, which is having two components. So one is IC, another is IM. IC is core loss component which is in phase with V1 dash and the product V1 dash IC gives the core loss, and V1 dash IC is equal to PC, which can also be represented as PC equals to I1 dash square into RC. So this RC is the core loss resistance, and the second component IM lags the voltage V1 dash by an angle of 90 degrees. So this is a reactive component. So Xm is the magnetizing reactance, which is related by this equation Xm equals to V1 dash by Im. So Rc can be calculated using V1 dash by Ic, and Xm can be calculated using this equation. Okay. Any question up to this?
Sir, I had a doubt in that ideal transformer.
Yes, tell me, what is your doubt?
Sir, actually, I need to see the equations.
Which equation?
Sir, it was there in the slides.
Yes, tell me.
Yes, sir. Yeah, this equation.
Hmm.
Sir, can you explain those again?
This equation, first equation is the applied voltage expressed in terms of the voltage drop across the leakage impedance, that is I1 Z1, and this V1 dash. Okay, what is this voltage? We know that the induced EMF across the primary winding is E1. Okay, so E1 lags the flux by an angle of 90 degree. Okay, now when this current flows, we can assume one voltage drop along the direction of this current flow, which is V1 dash, and this V1 dash is taken as the negative of E1, that means in opposite direction of E1, and this equation satisfies the Lenge's law. The Lenge's law, I mean Faraday's law of electromagnetic induction with the proper polarity, that is the Lenge's law. So according to Faraday's law, this when there will be some change in flux linkage, there will be some induced EMF, and from Lenz's law we get the direction of that induced EMF. So this induced EMF will be in such a direction that it will oppose the cause which is producing it. Okay, so here we can consider that V1 is in opposite direction to that of V1 dash. Okay, so V1 dash V1 will be in opposite direction to that of E1 dash as per Lenz's law. Okay, now to write the circuit theory equation, we must consider that V1, that is the supply voltage, which is the voltage rise, that voltage rise must be equal to all the voltage drop as per KVL. So V1 dash is considered a voltage drop which is with that voltage drop, another voltage drop, that leakage impedance drop, will give you the total applied voltage V1. Clear?
Yes, I understood.
Now normally so this is the exact equivalent circuit of a transformer. Here RC is core loss resistance, as I have already mentioned, and Xm is the magnetizing reactance, and this windings, two windings N1 and N2, they are to show the transformation of voltage and currents between primary and secondary windings. Okay, okay, so that is all about this equivalent circuit. Okay, if you have any question up to this.
Hello, sir.
Yes.
Sir, how magnetizing current and flux are in 90-degree phase?
Magnetizing current and flux, I have never said that. Magnetizing current and flux are in same phase.
You said something 90-degree flux is 90-degree phase with some current.
Induced EMF. Induced EMF. Two induced EMFs, E1 and E2, lags the flux by an angle of 90 degree. This exciting current has two components. One is IM, another is IC. So IM, recall the phasor diagram. This is IM, which is in phase with phi or phi m. This is IC, which is in quadrature with IM, and along this line we have V1 dash. Okay, and along this line we have two induced EMFs, E1, E2. So V1 dash lags IM lags V1 dash by an angle of 90 degree, and IC is in phase with V1 dash.
Okay, sir, got it.
Yes.
Sir, from equation you wrote IE equals IE dash IE it equals to IE plus IM.
No, no. IE is equals to IC plus IM. Phasor sum.
Okay, sir.
Phasor sum. If you find the resultant of these two, these two, you will get IE. These are phasor sum, not algebraic sum. IE is exciting current which has two components. One is core loss component, that is IC, another is magnetizing component, that is IM. Magnetizing component produces the flux phi or phi m. IC is responsible for the core loss, both hysteresis as well as eddy current loss. Okay. Any other question? So this is the exact or main equivalent circuit. Next we are going to study other equivalent circuits which are the modified version of this equivalent circuit. Okay, so you have to understand this one very clearly. If you have any doubt, you can ask.
Sir, how IC and IM are 90-degree in phase?
They are this exciting current, this current is the one of the component of primary current. I1 is the primary current, which is IE, another is load component I1 dash. Okay, this is also phasor sum. So this IE is resolved into two components. Okay, resolved means they are decomposed into two components. One is along phi, another is in quadrature with phi. That is why the angle is 90 degree. See, in practice, we cannot connect one ammeter here, one ammeter here, or one ammeter here. Practically, we can connect one ammeter here only and one ammeter here only. Okay, so this ammeter will read the primary current. Okay, I1. Now when this load, when there is, and this ammeter will read I2 only. When there is no load connected, this ammeter will read only exciting component of primary current, that is IE only, and this I2 will be 0 because there is no load connected, open circuit, so this ammeter will read 0 current. Okay, only IE, and when some load is connected, this ammeter will read I1, which is equal to IE plus I1 dash. Okay, so how to separate this IE and I1 dash, that will be discussed while we will consider or discuss the open circuit test and short circuit test, how to separate these two components. Okay, now the concept is we have the exciting current and they are resolved into two components, one along phi, another in quadrature with phi. That is why this angle is taken 90 degree. Is it clear?
Yes, sir.
Okay, so going to next, that is simplification of exact equivalent circuit. Okay, now we have seen that normally or we have learned the technique of referring any quantity or parameter to other side, from one side to other side. Okay, so in practice normally this secondary quantities are referred to primary side or primary quantities are referred to secondary side, so that we can have an equivalent circuit referred to either side, that means referred to primary side or referred to secondary side. Okay, so that is one kind of simplification which will simplify our calculations while using this simplified version of equivalent circuit. Okay, so we know the equation by which we can transfer any resistance or reactance or impedance from one side to other side. So here see the secondary resistance drop I2 R2, that is transferred to primary side. So this I2 R2, this is a voltage drop, and we know that voltages are transferred using direct ratio. So N1 by N2. If we multiply this voltage drop by direct ratio, then this voltage drop gets transferred to the secondary side, primary side from secondary side. this I2 R2, this is obviously the voltage drop of this secondary side winding. Okay, secondary resistance drop. So this voltage is transferred to primary side by multiplying it with the direct ratio N1 by N2. Okay, which we can write, use equation I1 N1 is equal to I2 N2. By neglecting the exciting current, we can have this equation. So from this equation we can write I2 is equal to I1 N2 N1 by N2. Okay, so putting this value in this equation, we get I1 into N1 by N2 whole square into R2, and we know that this R2 into direct ratio squared is actually the value of resistance connected to primary side, which was earlier in the secondary side with a value of R2. Okay, so R2 is the secondary resistance, when transferred to primary side becomes R2 dash, which is equal to R2 into direct ratio squared, isn't it? We have seen this transformation technique. So this
Yes,
part,
sir.
this part is actually R2 dash. Okay, so that means this secondary resistance when transferred to primary side, it becomes I1 into R2 dash. So R2 dash is equal to this. Therefore R2 dash is placed in the primary circuit and there is no change in the transformation between V1 and V2. So that transformation remains unaffected. Okay, this resistance R2 dash is called the secondary resistance referred to primary. So R2 dash is the, we can say it as the reflection of R2 from secondary to primary. Okay, so its effect on voltage transformation and current transformation remains same whether it is connected to secondary side or primary side. When it is connected to secondary side, its value is R2. When it is connected to primary side, its value will be R2 dash, and the formula to calculate R2 dash is R2 times the direct ratio squared. Okay, so now what will be the value of total resistance in the primary circuit? Primary winding resistance R1 was already there. Now we are adding R2 dash. Okay, so this is the total resistance now in the primary side. So RE1, that is the total resistance in the primary circuit, which is equal to R1, that is the winding resistance of primary side, plus R2 dash, which is the secondary winding resistance referred to primary. Okay, so this dash notation is used for denoting the referred quantities, but do not get confused with V1 dash and I1 dash. These dash notation are not for referred quantities, they are already assigned. V1 dash is the voltage which is equal to minus of V1, I1 dash is the load component of primary. Okay, is it clear?
Yes, sir.
Yes, sir.
Okay, so RE1 is called the transformer equivalent or total resistance referred to primary winding. Okay, so RE1 is the total or equivalent resistance referred to primary side. Now see this equivalent circuit which is referred to primary. Okay, so up to this part it is same as that of the previous exact equivalent circuit. Now this what are the changes or modifications made here? See R2 dash, sorry, whose mic is on, please mute yourself. Mute yourself. Okay. So R2 dash is the referred secondary winding resistance referred to primary. X2 dash is the secondary leakage reactance referred to primary. I1 dash is the load component of primary current, which is equal to the current I2, secondary current I2 when referred to primary side. So how this current is referred? Current is referred using the inverse ratio. Okay, so I2 when referred to primary side, it will be multiplied by the inverse ratio N2 by N1. We are referring to primary side, so here will be N1. Okay, all the voltages, the two voltages of the secondary side, one is E2, another is V2. These two are transferred to the primary side using direct voltage ratio. That is, these two voltages are multiplied by direct ratio N1 by N2, N1 by N2. So up to this, is it clear?
Yes,
How
sir.
these quantities
Yes,
are
sir.
referred to the primary side? So this is up to this is the primary side. This is primary side and this is secondary side. Okay. Now from this point to this point, we can connect the ideal transformer primary winding, and from here we can connect the ideal transformer secondary winding. Okay, so voltage across these two terminals is V2 and voltage here is V2 transferred to the primary side, that is V2 into N1 by N2. Okay, so all the secondary quantities are referred to primary side and the ideal transformer is drawn to the after this circuit to the right hand side. Okay, so now if you remove this part, that is also valid, because this part has nothing to do with this equivalent circuit. It only shows the voltage transformation. So here we are giving V1 voltage and across these two terminals we are getting V2. Okay, so now if we have some ideal transformer, then only we can get V2 output from here, but it has nothing to do with this equivalent circuit. Okay, so from this equivalent circuit we can remove this ideal transformer part. So this is the equivalent circuit referred to primary side. Is it clear?
Excuse me, sir.
Yes.
Can we put R2 dash and a X2 dash adjacent to R1 and a X1?
Sorry, please repeat.
Sir, can we put R2 dash and a X2 dash, the impedance and the resistance of the secondary adjacent to the primary resistance, means before the current division, I1 divides.
Yes, I am coming to that part only. For this circuit it is not possible, but that modification I will do. Okay, I am coming to that part.
Okay,
Up
sir.
to this, is it clear? Any question?
Yes, sir.
Okay, so next we are going to refer all the quantities to the secondary side, from primary to secondary. So R1 dash is referred to secondary side, R1 is the primary resistance. Now see, it is referred to secondary side, so N2 is here now. So while referring to secondary side, N2 by N1 is the direct ratio. Okay, this is important. This you have to remember always. Direct ratio means first you have to consider in which side you are going to refer. Okay, so while referring to primary side, the direct ratio is N1 by N2. While transferring to secondary side, the direct ratio is N2 by N1. Is it clear?
Yes, sir.
Yes, sir.
Okay, so this is how we are going to refer uh, the primary resistance to the secondary side. Therefore the total secondary resistance is this, which is the total equivalent resistance also. So this is the circuit. See, first the ideal transformer is drawn. So this section is the secondary section, which is same as that of the exact equivalent circuit. Okay, now all the primary quantities are referred to secondary side. First of all, consider V1. So V1 is referred to secondary side, multiplying it by N2 by N1. R1 dash X1 dash we have already shown, we have already seen. I1, see here the current is in inverse ratio. Current is referred to secondary using inverse ratio. Okay, V1 dash is multiplied by N2 by N1, direct ratio. IC dash, RC dash, IM dash, XM dash. These are already referred using the proper multiplying factor, that is either N1 by N2 or N2 by N1. Currents are by N1 by N2, resistance and reactances are multiplied by direct ratio squared. Okay, this current is also referred, and here we were having I1 dash, that current is multiplied by the inverse ratio, then that after multiplication it becomes I2. Okay, so I1 dash is the primary current, load component of primary current, so it is a primary parameter, so it has to be referred to secondary side using the inverse ratio, so N1 by N2, then that current is equal to I2. While discussing phasor diagram, I have mentioned that I1 dash, that is the load component of primary current, is not equal to I2. Okay, it is the equivalent. So this is the equation how we are getting the equivalent. Okay, while transferring this equivalent circuit from primary to secondary, then this load component has to be multiplied by the equivalent trans ratio. Okay, and while referring to primary side, this I2 current, this has to be multiplied by the proper trans ratio to get I1 dash. Is it clear now? Any doubt? Now tell me, which one is easier, transferring to primary side or secondary side?
Transferring to primary.
Obviously, because it deals with lesser number of parameters. Okay, while transferring from primary to secondary, we have larger number of quantities that has to be transferred to the secondary side. Okay, because we represent this shunt branch in the primary side only. Okay.
Excuse me, sir.
Yes.
Sir, why we transport RC dash and XM into the secondary side? It should remain in primary side because after core loss and magnetizing plugs, the voltage from primary will be transferred to secondary, and after secondary, there is secondary load under the transport primary resistance.
Okay. Okay, I got your point. Anyone else having this same doubt or same question? First of all, why we are transferring these parameters to the secondary side? The simple answer is these parameters are primary side parameters, isn't it? Now the question arises, why these are considered as the primary side parameters? Recall the current, primary current I1. It has two components. One is load component of primary current I1 dash, another is exciting current IE. So IE is primary current, isn't it?
Yes, sir.
It is a component of current, so it is a primary parameter, no doubt about that.
No, sir.
Then it has another two components. One is IC, another is IM. So this IC and IM are also primary parameters, right?
Yes, sir, got it.
Then RC and XM are also primary parameters, so they has to be transferred to the secondary side. Any other question? Okay, so this is the table by which you can, by using this table you can transfer all the parameters from one side to other side. So while referring to primary side, this primary winding resistance is already there, so secondary winding resistance has to be transferred using this equation. X1 is already there, X2 has to be transferred. This is the total equivalent resistance of primary side, total equivalent reactance of primary side, total impedance. I1 remains same, I2 has to be transferred, V1 remains there, V2 has to be transferred. Okay. Similarly, for refer to secondary quantities. Now with these quantities we also require to transfer RC and XM. Sorry. So while referring to secondary side, we have to transfer RC as well as XM using these two equations. Okay. So that is the transformation of exact equivalent, simplification of exact equivalent circuit. Now further simplification. So this is the generalized form of equivalent circuit without any ideal transformer. As I have already mentioned, we can remove the ideal transformer. Okay. So here this is the generalized equivalent circuit where for simplicity we have dropped the referred quantities notation. So by observing this, you cannot say in which side this transformer is referred to. Okay, you have to mention it. Then we have dropped the complex notation. So JX1, JX2, those and JXM, those notations are dropped also, and also the phasor notations are also dropped. Only the magnitudes and the ideal transformer is not shown. So this is the more simplified and generalized equivalent circuit. Okay, so while drawing this equivalent circuit, we have to mention in which side it is transferred. Okay, because by observing this circuit you cannot say in which side it is transferred. Now here you can see this point, the current at this point, the primary current at this point is getting divided into two components. One is exciting current, another is the load current. This I2 is actually the load current, which is in actual exact transformer, exact equivalent circuit of transformer, which is the I1 dash, and I1 dash and I2, how they are related, that we have already discussed. Okay, so this exciting current, this also I have already mentioned, exciting current IE is about 2 to 6% of I1. Okay, that means with respect to this total value of I1, this exciting current is very small. Okay, so we can either exclude it or include it while calculating the voltage drops across this primary winding resistance or secondary winding resistance. Okay, so we can shift this point to connect it here or connect it here. Okay, so we will be seeing those two modifications. So consider this circuit. Here this point is shifted here. So if we shift this point here, what is the meaning? The meaning is the I1 is getting divided at this point. So what happens? From this path IE is flowing, and from this path I1 dash is flowing, which is equal to I2 by some relation. Okay, so that means through this part a lesser current is flowing, because I1 dash is less than I1, obviously, because I1 is the total current and I1 dash is part of it. Okay, so lesser current is flowing through this winding resistance and leakage reactance, so there will be a very small less voltage drop. Okay, previously the voltage drop was I1 Z1. Now the voltage drop is I1 dash Z1, which is less than this. So we are considering a small a little less voltage drop now. So for in doing that, we are getting this circuit where we can represent the two winding resistances together by only one resistance, which is Re, that is the equivalent resistance, which is equal to R1 plus R2, and Xc, that is the equivalent leakage reactance, which is equal to X1 plus X2. So this is one modification. Here we have excluded the voltage drop due to exciting current, primary voltage drop due to exciting current, because now the exciting current is not flowing through this path. So we have excluded that part. Is it clear?
Yes, sir.
So we can do the other way, in another way, that is we can shift this point to this point. So if we do that, what happens now? Now the total current I1 is also flowing through the secondary leakage impedance. After flowing through this path, then I is getting divided into that means I1 is getting divided into two parts. One part is IE that is flowing through this path, another part is I1 dash, which is related to I2 and flowing through the load. Okay, so here what happens, through this secondary leakage impedance some extra current is flowing. So what current is that? IE amount of extra current is flowing. Okay, because the current is getting divided after flowing through this primary current I1 is getting divided after flowing through this path. Okay, so if we take exact equivalent circuit, this IE never flows through the secondary leakage impedance, but if we take this approximation, then IE flows through this secondary leakage impedance. So here we are including some extra voltage drop. Okay, and again we can show the winding resistance by a single resistance and leakage reactance by a single reactance. Okay, so Re is equal to R1 plus R2, Xc is equals to X1 plus X2. Okay, someone was asking this question. Have you got your answer?
Yes, sir, got it.
Okay. Okay, time is over today. Up to this, we have another modification, some more modifications also, that will be discussed in next class. Now just a minute, let me take the attendance first.